Last thing, and I just want to show us a little bit about the stress fields around a crack. And just to help me visualize, I think of a crack, you can see now that I'm a little more creative with my cracks. I don't draw them with straight lines for the reason I told you. I don't see them at that size scale over there. And I have a plastic zone there, and I'd like to know what happens in terms of the stresses and strains around the crack. And so just to help me, I draw my little specimen to help me visualize what happens. And of course, as I pull this in tension, then of course there will be a big plastic strain way out here someplace. And if I look at the entire stress field in front of the crack, then I will have high stresses in this plastic zone. And then of course they will decrease and reach the average stress. And then of course when I unload this, something different will happen. And then if I am here and I unload this, it will unload elastically, and then I am left with some residual plastic strain here. But because of constrained plasticity, all the material which surrounds this plastic zone will force the displacements here back to zero. And when you force those displacements back to zero, the only way to do that is to have a big compressive stress. So in any crack that we see, if there were a crack in here and I loaded this and unloaded this, then there would be a big compressive stress around here. Can you grow cracks in compression? Simple enough question. No. Yes. I like these two answers. I like when there's multiple answers. The other thing, when I teach, particularly undergraduates, I like to bet a beer with them because I always win. I've never understood why they want to bet. I do understand why they like to bet with me. Here's the reason why. Okay, I win the bet. Okay, some afternoon after school, I go have a beer from them, and they buy me a beer because they lost, right? But somehow the rest of the evening, it always seems to be my turn to pay. So I know why they lose these bets in class. But I'm always happy to go out with them. So it's yeah. Anyway, so yeah. Oh, I'm very tricky. You know, I might do something like take two bars in my hand like this, and then I'm pulling the bars like this to give some visual cue. And I'll say, you know, which one is stronger or things like that. And in case they guess the right answer, I'll say, you know, I'm pushing this in compression and it's a buckling failure. And of course, the buckling load is independent of the strength. I win. You know, fine. So back to, okay, your eyes laughing again. Good. You know, it's hard to keep people's attention later in the afternoon. So, you know, hard for me to imagine how I could grow a crack if there's compression at the crack tip. It's easy for me to see how I could grow a crack under compressive loads. That's the difference, right? So if you view what happens at the crack tip, so let's do a little thought experiment. I have one plate here, and I take a second plate and put it on top. So I guess you could say the interface is like a crack. Sure, mechanics-wise, it's exactly like a crack. I can press on this forever and nothing happens. I can press on this forever, nothing happens. The only way I can fail these two plates is to put the smallest amount of tension, and then I can open this up. So if your view about whether you can grow cracks in compression, right, is the stresses around the crack, then no. But if your viewpoint is external loads, then it's easier, because it's very easy to have external compressive loads that produce compression at the crack tip. Even in the case of something like concrete. So you say, aha, you can do it a different way. Look, when I compress this in a concrete cylinder, I get failure off on 45 degrees, and I get shear failures and all that kind of stuff. That's true macroscopically, but what happens as the aggregate presses by one another, you actually get a bunch of opening forces. So I think it's safe to say you need opening forces to get a crack to grow. And we'll see that that's the basis of a lot of the multiaxial fatigue models. That the stresses that are acting on the crack matter, and they matter a lot. So here's an example of this closure stuff. Here's just something that was loaded from 0 to 350. And on the left-hand picture, you can see how everything is tightly closed. On the right-hand picture, you can see how this crack is opened up. And this is the level you need. You need a lot of tension, right, even to get the crack open. And this is not quite open back here. It always is closed a little bit back here. The crack tip is up at the top, and there's a little opening just behind the crack tip. But this crack can't grow until this whole crack starts to open up. So we have lots of experimental evidence that that's true. Right? So when I look about something, I look at the damaging portion of the loading history. It doesn't matter if it's simple uniaxial loading or a complex multiaxial history. There's a damaging part of the history for which the crack tips see tension. And that's very damaging, and all this stuff down here is non-damaging, right, because the cracks are held tightly closed. If they're held tightly closed, they can't. So far I've talked about these macroscopic cracks growing, and I've really talked about mode 1 opening, and of course we can have this different modes of loading, 1, 2, or 3. Of course the opening mode 1, you can have mode 2 loading in a plate, but it's difficult to get. You can have mode 3 loading in a plate, which is tearing, which is pretty easy to get. It's also easy to get modes 2 and 3 loading in torsion of a cylinder, because if I have a thumbnail crack in the cylinder, on the surface that you see is always loaded in mode 3 and mode 2, and at the bottom of the crack is always loaded into mode 3. Let's think about now growing a crack in mode 2. It's difficult. First of all, here's mode 1. So I showed you earlier this idea about shearing back and forth, and that can leave some striations. This is in steel, and so here you can see the individual striations across the material. It's a very beautiful picture. It comes from my master's thesis. I told you I got my master's thesis in material science, and so all the graduate students knew that in the material science department, the professor always found some pictures that he didn't like because the edges were fuzzy or something like that. Right? It's just what professors do. I do it as well. But of course the graduate students are smarter than the professor. The professor has a little more experience, but the graduate students are always smarter. So none of us put in the best pictures the first time around. We always put in a slightly fuzzy picture, and if you put that in as your first pictures and the others looked okay, professors say, this one just isn't good enough. You say, okay. 2 or 3 days later you would paste the good picture you already had in there, and he'd say, oh, much better, and sign the thesis, and you were done. It worked, right? Look, here I am now, many years later. You never thought of this trick. I have more to tell you about it. Yeah, this just works. This just works. They always complain about the pictures and so on. Yeah, those are striations in steel that I took in 1970. I had to show it. Yeah, it's a long time ago. Yeah, I evaluated crack growth in different kinds of welded joints and all that kind of stuff. Published a paper, put my advisor's name on it, even though he was clueless to what I was doing in the lab, and it just worked. Anyway, but look at how clearly defined that is, and you can imagine this crack growing, and you can imagine how this is opening up. So, I only tell you that story because this is not my picture. You see over here, and the color is not balanced, and you can see just really an awful picture. That's just an awful picture. But it's the best one I have. And I'll tell you the story behind this picture. This is a Japanese picture. This is one of Professor Murakami's graduate students. I mentioned earlier that I go there for a few weeks every year. And I work with the students, which is great fun. But I have to be careful what I say. So I was talking to this student, and I told him, I said, next time you are in the library, get this article, because it related to what he was doing. And that afternoon I came back, and here's the article in the box with a little note on it. I did what you demanded. So next week when he came to see me, then I told him, I said, demand is a very, very strong English word. It's I didn't demand this, I just, okay. And he looked at me and he said, "You are the professor, I did what you demanded." And so I learned to be careful. And it was his work, and I just mentioned him. I said, "This is a really good picture, and this is a picture of a crack growing only in mode 2. It's actually shear of the plate. Really hard to do," and so on. And I just mentioned him. I said, "Next time you make some pictures, can you make a copy of these two for me?" The kid was probably up all night because there's a stack of pictures like this for me the next day. I know why I like the students in Japan. They maybe are not so creative, but they work hard, and they would just do these. I can't imagine any of you doing that. I can't imagine any of my students doing that because it's not in the Western culture, right? Demand is a very weak word in the Western culture compared to Japan. But look at this picture. First of all, right? First of all, by the way, you've now learned my style. I tell you these funny stories because then I get your attention to tell you something you might remember. So yeah, that works too. Look. Cracks growing along here. Look at all this severe rubbing that happens here, right? You can see the tracks as this stuff is being pulled by. And imagine I have the top and the thing like this, right? No features on here at all, right? It's really, really hard to do that. Imagine if I take my little cartoon here, I'm trying to shear this back and forth, and again I have a cracked surface which is not really flat, but it's trying to shear itself flat. Look how difficult that is, right? That's really, really hard to do compared to opening this up in detention. So what you will find is that crack growth in shear, longer crack growth in shear, is very, very difficult. Right? The rates really are slow. But what would happen if I'm shearing this back and forth, and now I put some tension on to open up this crack and get rid of all this crack face friction? Right? Just a little bit. Right? I don't need a lot. I put a little tension on this to get rid of the crack face friction. Right? That crack's going to be able to go really easily, isn't it? It's going to grow very, very quickly. Very, very quickly. And we'll see this tomorrow when I talk about the fracture models of what happens to growth. That's the key, right? The key is we think about, I'm going to grow cracks, micro cracks or otherwise, and that process is going to happen in shear when they're small. But in the shear mode, there's just a lot of friction. A lot of friction, and you can see it in these pictures. You can just see the evidence of that. And that's an important, maybe the most important part of the driving.
Sorry?
Yes?
Why is it so difficult to get a picture like that? I mean, what's the...
Why? Oh, the picture's easy.
Yeah, I mean, okay, but...
It's getting a crack to grow in shear.
I mean...
It's difficult to get a crack to grow in pure shear.
Okay, oh, okay, yeah.
That's the hard part.
Okay.
Because what will happen is, okay, so I think about all of these funny shear specimens, right? So, okay, so you have this funny one that the composites people use. And then, of course, this zone is in shear. And you say, fine, it should be really easy to grow a crack in shear. And if you believe the mathematics, that's true. But I spent about 5 years trying to do this in composites. Never successful. Never successful. And the reason you are not successful is this is not the real boundary condition. Because in order for this to be the boundary condition, then this has to have no bending at all. So this has to be fixed from any kind of bending loads. And it's impossible to do that experimentally. When you actually do these kinds of things and try to grow cracks, you get this and then the things come off like that. Yeah. So the only way to grow a shear crack is to try to do it in a tube. But even in a tube, they try to turn and grow into tension. That's the difficulty of getting a long shear crack. A short one is easy. If I want to get a shear crack that's a 0.5 millimeter long, that's pretty easy. Getting a shear crack to grow in shear that's 10 millimeters long is really, really hard. And by 10 millimeters, I don't mean along the length, right? It's easy to get a 100 millimeter crack in this, but maybe it'll have a depth of a 0.5 millimeter. But to get something that goes inside is just really, really hard. So that's the problem. Yeah. Okay, so let's look at what happens. A little summary about what happens in materials. And we'll look at a couple different states of stress. So this is plain steel, and percentage of the lifetime on the left-hand side, and of course fatigue life on this hand side. And so this is the result of just summarizing lots of different experiments and lots of different observations. And this solid black line is how long does it take to get to a crack that's 100 microns long? Now what fraction of the height is there? And this is what happens afterwards. These are pictures of what happens. And so if you test with a lot of plastic strain, then the lifetimes are low. And of course, so let's just look in here. So what will happen is that in tension, maybe you spend 10% of the lifetime, and that gets you a crack that's 100 microns long. And after that, then the crack grows, and then finally will failure. Here's a picture of what that looks like. And what you see in this steel is you see a whole lot of cracks in here. Right? And the final failure is like tearing perforated paper. There's lots of little microcracks that grow and interact with one another and so on. And the reason that there's lots of little microcracks here is that there's so much plasticity that you can nucleate a crack in every one of the crystals without regard to its crystallographic orientation. I'm just overwhelming the problem with plasticity. And then we can look at what happens out here at long lives, and so out here at long lives, millions of cycles. Okay. Right. Maybe 80% of the lifetime is taken up in nucleating a crack to 100 microns, and 20% of the lifetime is taken up into growth. So as I mentioned a few times already, we're going to see how I'll ever build a single model that works. Because the physics here is very different than the physics here, and what's important. And then, of course, you have the practical cases in the middle. It spends some time growing in shear, some time nucleating and growing in shear, and now the majority of the growth is in tension. So there's 3 possible failure scenarios just from that. Here's the same material, only now it's in torsion. So I twist the bars. And as I twist the bars, then you see the same kind of behavior for shear. First, let's look at this line, 100 micron crack. And what you see is that the cracks nucleate, but unlike tension. So remember tension, this curve hooks up like this, and most of the lifetime is spent nucleating the crack. Here, cracks always nucleate. Right? So fatigue crack nucleation and growth out to 100 microns is a shear-driven process. Of course, the shear stress in torsion is huge. So remember, the shear stress in torsion is equal to the tension stress. The shear stress in tension is only half of the tension stress. Right? We'll see that in a few minutes. So the cracks always nucleate, right? But they don't grow very fast. And that was my reason for showing you the pictures. Right? They don't grow very fast because you have all of these stresses which are acting on a crack face. A lot of the modes are taken out by friction. And there's a couple of different modes in shear. When you have a lot of plastic strain, you just nucleate so much damage that this again tears like perforated paper. And in fact, the end failure of this actually tears off at 45 degrees in the last cycles. And out here at long lives, you get these very long cracks which appear very long on the surface, but of course that's not the crack length we are interested in. We are interested in the crack that goes this way into the depth, and that's not a very big crack. You see something that's very, very different. And then you can look at stainless steel in torsion, and you get a similar picture. You get a picture like this. Cracks nucleate really easy in torsion for the same reasons we said before. And now at shorter lives, you always see cracks which get to be very long on the surface and try to grow into their depth, and they do this in shear. And if you look at what happens in longer lives, these cracks nucleate in shear, but then they turn and they try to grow as principal stress-driven cracks. So now I showed you that it's a little bit complicated, so I've shown you at least 3 or 4 different failure modes to model the physics. And now I was able to change the physics just by changing the material from a piece of carbon steel to a piece of stainless steel. So now I know that I not only need models that work for different failure modes, I need to understand what failure modes go with what materials. So again, the hope of a universal model and somebody telling me they have the very best model, I put in my finite element models, let's say, and always predicts the right answer, it makes me laugh. not much happens in tension. It's hard to nucleate them at anything in tension, and then they grow into failure. This is the ink canal. So again, in torsion, you nucleate these pretty much like the steel. You get lots of cracks that run in that direction. Like, they're not very deep, and it's really hard to grow these shape cracks. And this is what happens in tension. So at long lives, again, you spend most of the time trying to nucleate and get a crack to 100 microns or so on. And once that crack nucleates, if you have a lot of plastic strain, it tends to be dominated by the shear stresses and linking up of all of these microcracks from the shear stresses. And if you're at this intermediate life range, it nucleates, and then it spends a lot of time growing as a principal stress. Okay.
So now we move to the next.
Yeah, you can help me. The graduate students, and remember I told you, if I fumble around long enough, someone will help me. Second one. Oh, how did you get it so quick? All right, thank you. So I've told you about what I see in the lab and a little bit about the physics of fatigue. So now I want to start into the modeling of these, and we've already talked about that there will have to be several of them. So let's look at the stress-based models. And so if I just summarize what I spent the last hour talking about, then fatigue cracks do nucleate in shear, no matter what mechanisms we look at in detail, but macroscopically they nucleate in shear because that's what's required for plastic deformation. And then after they nucleate, they kind of have a choice. There's a choice to grow either in shear or in tension. Eventually they'll always be in tension at the very end, but that might be the last few cycles of life for which we are not too interested. And so now if I look at doing fatigue analysis, I have a standard way of doing all fatigue analysis, and here's my little template, in that I have to know something about the materials data. And of course, if I want to analyze something, I need to know about the geometry, and I need to know about surface loading, and I want to make an estimate of the fatigue life, and I can choose the analysis. So it seems to me that the most important part is here, right? I can't do anything about this. They are what they are. Maybe I have to make some guesses or approximation, but I have different ways of analyzing things. And the terminology I like to use for the different ones is I like to think about lumping all the things that are based on stresses as the driving force to be the stress life approach, and all those that are based on using the strains rather than the stresses of strain life. And then, of course, we might consider fracture mechanics and crack growth directly. And I have my little cartoon, so think about I have this little cutout geometry that we talked about before, and I look at the different ways of doing things in the different models. You know, in stress life, we just assume everything is elastic. And in strain life, we say, fine, we have to somehow deal with the plastic fields in front of the cracks and how cracks grow there. Or finally, I could think about that a crack forms in the structure, and I just have to deal with crack growth, and so I just draw a little schematic of a compact tension specimen. And depending on where you go to school or where you go to work, your view of fatigue generally falls into one of these three different classifications. And so I'd like to take, before I actually go into the stress-based models, I'd like just to take a few minutes and just talk about the three global approaches first, right? How do I choose to solve the problem? And not unlike the problem that Paul Paris faced, right? He was given a problem in fatigue, and he had no choice about his solution. He's in a school, all the professors there are working on fracture mechanics, right? He's taking classes from all these professors. He's now given a fatigue problem, so he immediately goes here. Why wouldn't he? Right? Why wouldn't he? But that's not the solution to all problems. By the way, the fracture mechanics approach would be pretty useless at making an estimate of the life of the crankshaft I showed earlier. Right? And it would be pretty useless because that has to undergo 1 billion cycles of fatigue in it, so it's pretty useless. Okay. So I try to tie these approaches a little bit to the physics. And so if my approach is to look at doing everything with stress life, the physics I'm really trying to model is crack nucleation, because I say this is the dominant part of the physics. Right? Majority of the lifetime is spent here. And that means on a size scale, that's something maybe 10 or 100 microns in size. By the time a crack gets to be 100 microns, it's certainly nucleated and it certainly will grow. And I think about strain life. Strain life is really all about microcrack growth. Cracks happen early in the life because you have this plastic strain, but they're tiny and they grow and interact with the microstructure, and they start and they stop and all that kind of stuff. And so I liken that to saying, well, okay, maybe I have things that might go between 10 microns and a millimeter. And then finally I think about what happens when you have visible cracks, and of course that's macroscopic growth, and that's something for which the size scale that I deal with is much bigger than a millimeter. Right? So why does any of this work? Well, it works when we have the right similitude, and that is we want to study somehow materials, and we want to take what we learn from materials, and we want to use that to get the likely performance of the structure. And so that means we have to have the same failure mode. So let's just think about what happens in the stress life model. Airbus of some sort, isn't it? The only Airbus I recognize is the A380. I don't recognize any of the others. I can't tell the difference between an Airbus and a Boeing airplane by looking at it. I'm sure there are some characteristic shapes that an expert would know, but I don't. There must be one that size. And there's my little cartoon of my physics, right? Is that a good model for this? I want to make an estimate of some part in this thing, right? I've been called upon to do that, and I want to make an assessment of this, and of course, my viewpoint of the problem comes from testing things like this to get some material properties, and of course that's what I'll end up, something that looks like that, and I can choose whatever models I want, whatever math I want, but the basic idea comes down to, is this a good model for this? Because you know, if this is not a good model for this, why would I expect to get the right answer? Luck, right? It's like the student who doesn't come to class, right? Does very poorly on the examinations. The final exam day comes, and the student, instead of studying, just prays for a miracle. You know, chances are possible, but not too much, right? Not too much, but it is possible. So if we throw out that load case, it's possible, right? Yeah. Is this a good model for this? What do you think?
It depends on which side you want to design. If you want to design for unlimited fatigue, well, maybe it may be a good model, an acceptable model.
Sure.
But if you want to be light and have a good assessment of the lifetime, it's an appropriate model.
Yes, but it would depend on it. Yes. Okay. Yeah. You asked another question. Is this a good model for the airframe? Probably not, right? So if I think about the size of this airframe, and I think about all the little cracks that are there around rivet holes, and I think about cracks that are there because when they manufactured it, they pulled a little bit too hard, and so on and so forth. It's a terrible model. By the way, you say about cracks being there, maybe you remember, I don't know, DC-10s. So a DC-10 is the airplane that has the engine in the tail of the airplane. And the DC-10s had an airplane crash because an engine fell off over Chicago. And you know, a lot of people were killed, of course. And that happened and that was a crack that was about that long. And this was in an area of the airplane that was never inspected because it was designed for stiffness to hold the airplane. And what happened was American Airlines found that when they replaced the engine, if they replaced the engine and pylon at the same time, it was much faster and easier. And in the process of replacing it, then of course you have this big engine, this big mass, and the pylon up here, and you're doing this trying to get everything aligned. And all the cracks happened when they did maintenance, when the plane was on the ground, not flying. Right? So I believe there are cracks in structures. So if you ask me anything about this airframe, then I would say this is horrible. But how about something that's actuating one of the flight surfaces? That's what you said. Look, where are the parts of the airplane that have to have a really long life? And so if I look at some steel part in here actuating one of the flight surfaces going up and down all day, it's probably a pretty good model. Because in order to have very long life, the physics is I have to be sure that the cracks don't nucleate. I have to keep them out. And keep them out, right? If I had one of the actuators, then the actuator that runs one of these flight surfaces would be very carefully ground and precision machined and all that kind of stuff. Unlike everything in there and here. And then look at the engine components. How many cycles are on the rotor of the engine, right? It's huge. It's huge. Or how many cycles are on a turbine blade. So this is a good model, but it has nothing to do with the size or shape. Right? This is a good model because the physics is the same. What parts of this really big structure is the failure physics governed by the nucleation of cracks? And so this approach will work very well. Very well. And now I can go on and I can choose, oh, what is the very best stress life model to use and all that kind of stuff. Right? The secondary in terms of getting the big picture correct. So that's stress life modeling. Let's look at it a little bit. So it's easy to do the analysis, right? You choose some things about the materials SN curve, and then we have some modifications for surface finish and so on. And we know about stress concentrations, and we know about loading, and everything works. So what we don't always think about is the first one. The real assumptions behind that is that all the life spent in nucleating cracks. And that means that all the deformation must be elastic. It must always be elastic. By the way, how about applying this to the fasteners? Let's apply the stress life approach to one of the fastening bolts. All right? So I make my best drawing on the bolt. No, not too bad. Yeah. You are to imagine that this is a beautiful three-dimensional pro-engineer drawing in multicolors. Okay. Fine. Right. Will the stress life approach work on this? Because after all, a bolt, there might have to take a lot of little vibration cycles out there, and I certainly don't want to inspect all of the bolts. So will it work? Is the physics correct? Well, let's think about it a moment. What?
Nasty question.
What do you mean nasty questions? Yeah, the best and brightest PhD students, right? You should know these things right away. You know, this might be one of the questions, like my exam question, where you could just look up the answer on the graph, right? Look, I mean, just think about this a minute. You know that if you use a bolted joint, you need to preload the bolted joint or else it doesn't work. Right? So you have to pre-torque this. Right? If you don't want to think about the airplane, think about my new Lamborghini, right? Then I think about the heads on the engine to my new Lamborghini that has, right, very long rods on it actually, and I tighten them all down and so on, and you have to have the correct preload force and so on and so forth. So there's a big preload force here. And the preload force here is about 80% of the strength. So the stress is, statically is 0.8 times the strength of the bolt. Fine. But that's the nominal stress. How about the stress concentration factor for threads on a bolt? Approximately 3. Good answer. 3 is a universal answer, by the way. If you don't know the stress concentration factor and you guess 3 to start with, nobody can argue. They can say, oh, I think maybe it's 2 or something like that. But you know, 3 is the good starting point, always. Always. I have to be careful making those kinds of remarks. Not to you, but when I teach, because I get back those funny things. You know, just as we were talking about giving quizzes, you know, I gave a really complicated problem, and when I gave the homework, and I said, yeah, you know, if you want to just check your answer quickly, just take the biggest load cycle, calculate the life, and divide by half. That should put you in about the right range. And I just mentioned that as a helpful hint on how to do the homework problem. And so, of course, I gave a similar problem in the exam, and much to my amazement, I started to get in the exam, and I started to grade it in the beginning. Sosie's rule. Ignore everything, just take the big cycle and divide the answer by 2. Well, I had to give credit, of course. So I'll be careful. Yeah, 3, right? But look, so if the stress concentration factor here is equal to 3, and I'm already at 80% of the proof strength, I'm now at 2.5 times the strength. So the stresses in here are 2.5 times the strength of the bolt. So obviously they're all broken. Or maybe I should never preload things. But I can assure you my new Lamborghini, or Ferrari, it doesn't matter, right, will not work unless I preload everything, and certainly the airplane wouldn't work. And of course what's wrong with this is this one, isn't it? What's wrong with this is we know that if we have a bolted joint, the reason we preload it, and the reason we can tolerate these high values of KT, is that every one of these bolts will be plastically deformed at the root of the threads, and that's why it works. Right? But if I choose to analyze that with the stress life approach to fatigue, the answer I'll get will be absurd, right? Because I'm violating one of the major assumptions that have been behind it, right? Bolts essentially develop cracks on the preload cycle. Right? Every bolt in there has got a little crack in it, and they grow very slowly to fit. Okay? So those are the assumptions that maybe we don't think about them, but that's the assumptions we make. That means a nominal stress and material strength control of fatigue life. And to make all this work, you have to really understand about these little stress concentrators. So there are a lot of advantages to this. It's really easy to assess the changes in material and geometry. And you should also not forget that there's a large empirical database. You know, we've been doing these kinds of tests since the time of Voller 150 years ago. In 150 years, we've accumulated a lot of experience and data in it. So, limitations, we already talked about this, but the limitations really are, in many situations, you have plasticity. And if you get the plasticity wrong, then frequently you get the mean stresses are an error, sometimes of the wrong sign. And of course, a limitation is you really do need to understand what happens around stress concentrators, gradient effects, and all those kinds of things. So that's the stress life approach. So now let's look at the strain approach. So we do the testing a little differently. We test between fixed strain limits, actually fixed displacement limits, and doing it to test specimen. And so then I asked the same question before, is this a good model for this? And of course we come up with the same answer. Of course it is. For some parts. And those are parts for which we have a lot of plastic deformation. And again, what we're really asking is not does this resemble this in terms of size or shape, but in the physics. And so the physics here is one where because I have plastic strains here, then I will nucleate small microcracks early on in the lifetime. And these small microcracks will grow and they will interact with the microstructure, and eventually they will turn into big cracks of several millimeters, and when they do that, they will rapidly go to failure. So when I have this view of the physics, what parts of this have that failure physics? of the most likely parts in the vehicle?
Suspension.
Suspension parts. Yeah. Where else? Engine. If I want to find cracks here, the best thing for me to do is to go into the parking lot and take a look at the engine. And I believe I will find cracks in almost every engine. And the place I will find them is I will find them in the intake manifolds. Actually, not the intake manifold, but at the valves in the exhaust ports. So every time you start and stop your car, it heats up. There's this very small bridge in there that undergoes a tremendous thermal cycle because it's restrained by all the cool material around it, and they crack almost right away. They crack almost right away. Now, I had this problem on one of my cars. I had a Chrysler car, and I was invited to give a seminar to the Chrysler engineers. And so it was a big room, maybe 100 engineers there. And you know now how I like to tell stories and draw pictures. And so I walked over to the blackboard and I drew a picture of the famous Chrysler minivan that I had. And I drew a picture like that and said, oh yeah, I have a vehicle like this. And I said, oh, yeah, oh, thank you for buying one of our vehicles. I said, yeah, you know, I was out with my vehicle and it overheated. And then I paid and I had to have my car, and I towed my car to the dealer. And the dealer said, oh, the problem is that you have cracks in the heads on both sides. I said, well, okay, just fix it. I mean, it's true, I had 100,000 kilometers on my car, so it's okay. It's okay. By the way, I think now the lowest, right now, between my wife and I, we have 4 different vehicles. The lowest mileage car, I think, has 200,000 kilometers on it, so I just have them forever. So anyway, they wanted me to buy it. Anyway, so I bought that. All right, I had this, and so I said, okay, so this happens. This happens. I said, but what made me angry was the dealer said that it would take 6 weeks to get the parts. 6 weeks. And I said, you know, one of 2 things happens if it takes 6 weeks. First thing that happens is either this is such a rare failure that the dealers don't keep the parts. The other possibility, of course, is it's such a common problem that no dealer has the parts left. And at that moment, there was complete silence in the room. So I knew the answer was the second part. And afterwards, somebody came up and says, oh yeah, you shouldn't have mentioned that. You know, this is a really touchy subject right now, and so on. They're trying to decide, and so on. Anyway, the net result of that, it took 15 years before Chrysler invited me back to give seminars. So there's a long institutional memory sometimes. Yeah, so I'm a little more careful now. So I can say whatever I like, positive or negative, about Lamborghinis and Ferraris, because I know I never will own one. Anyway, yeah, so, but you know, that's a really good example where this is the right physics, isn't it? Lots of plastic strain, and I don't have to undergo very many cycles. I don't know, right? Very few, right? Maybe 2 times per day I start the car, and if I keep it longer than 5 years, it's much longer than average, even though I've had mine much, much longer. Yeah, so there are lots. So let's look at what this does then. Right. So I have the same analysis template, right? So the real part of doing fatigue is really understanding what to do, right? Same loading, same geometry. The only difference is I need a little bit different material property now that gets all of this plasticity. But the inputs are the same, and of course this part doesn't. This I'm not going to do longhand either, right? This I'm going to shove in some computer, so it's just as easy to do one of them versus another. Right? And so the assumptions behind this are that it's really these local stresses and strains, and what's important is the plasticity around the stress concentrators drives the process, just like this, right? A very important part of the mechanics of this bolt working is the relieving of the stresses around the stress concentrators by plasticity. that didn't happen, then bolt and joint wouldn't work. By the way, that's the reason you don't make bolts ever out of high-strength materials. If you made a bolt out of a very high-strength material, these high-strength materials have very limited ductility, so I don't have much tolerance for plastic strain here. And if I don't have much tolerance for plastic strain here, these things fail when you put them together and assemble them. So we see good examples of it. So the advantages are plasticity and mean stress effects. So there are some limitations, of course. This idea about how to deal with notches is still largely empirical, and I just put that as an empirical notch factor. And the other place this doesn't work very well is in long life situations where surface finish and processing variables are very, very important. Now, I'm not used to the valves. It's all right. Okay, I can talk more about it. All right. So, you know, if you have long life situations where surface finish is important and processing variables, why wouldn't this work? You know, I said for the stress life approach to be valid, everything has to be elastic. And if everything is elastic, it's a very easy transformation between the stresses and strains, isn't it? So at least conceptually, I should always be able to work in strain. I never have to worry about stresses. I can just worry about strains, right? And if I believe in all the plasticity models, which I do actually, I can do a good job of going from stress and strain even in the plastic region. So why not just always work in strain, and I can eliminate one of the approaches and say, look, I have a standard way of doing it. Well, you know, that's a true statement, but the process doesn't work. Why doesn't the process work? Well, the process doesn't work because all the material behavior comes from testing in a situation where plasticity dominates everything. And everything is based on material behavior having the right physics. So if I test in a region dominated by plasticity, and yet at very long lives, the failures are governed by the microstructure. Microstructure is not so important than plasticity. Microstructure is not so important. So the real difference between the stress and strain approach at long lives is whether or not you have incorporated all the microstructural features into the material database. That's the real difference. Mechanics-wise, it doesn't matter, yes.
But you can nevertheless work with strains.
It's no problem mechanics-wise, but it's the underlying materials data.
Yeah. Well, you just have to include more variables into the calculation.
Yes, but that doesn't happen. So if you use the strain approach, then people will say, okay, I have all these tests and I have all these plastic strains and I plot the plastic strain life and elastic and so on and so on and so on. But that's a failure that's dominated by plasticity, not by the microstructure variables. But you're right, computationally it doesn't matter. It doesn't matter. We'll see tomorrow, it does matter in the choice of theories, whether you work in terms of stress or strain. But concept-wise, it really doesn't matter, stress or strain. But it's in the input data. It's in the input data. Anybody who runs stress life kind of testing worries a lot about surface finish, residual stresses from processing, and all those things. Okay, finally we can look at crack growth. So those who work in fracture recognize those kinds of specimens. So the biggest specimen is about 1 meter square. And the smallest specimen inside there. And of course, if you have a big welded structure, then that's probably the best approach to use. All kinds of cracks in that. But you know, my analysis template is pretty much the same. I need to know some things about the surface loading to make this work. I need to know what it looks like, only now I'm going to do some slightly different calculations in that rather than calculate things and get the stress concentration factors or deal with the stresses at different nodes, I now need to know things about the stress intensity factor, but it's calculated from the same theory of elasticity stuff, so that one's easy enough. And now I need a little bit different material data. And so you can see if I use my template for the 3 different ways of looking at fatigue, What's really different in all of that is really different just here, in the material data part. And that's that material data was trying to capture different kinds of physics. The SN material data tried to capture the physics of nucleation of cracks. Strain life stuff tried to capture the physics in the database of materials about the growth of little microcracks on the order of the microstructure field. And of course the physics here is you're trying to capture the growth of cracks in the microstructure independent region, right, when they're big. Right? That's the real difference in how you approach fatigue problems. There we go. See, I'm learning to read Italian already. It works. All right. So now, the major assumptions are that the nominal stress and crack size control fatigue life. If you look at the practical implementation of this, getting the nominal stresses is relatively easy compared to this, and we don't really know so much about what the crack sizes are in structures. And I guess this really is the only way of dealing with cracks. As far as I know, no one has a better way of dealing with cracks. There are some people who try to build universal theories now, and they try to say, gee, I'm going to model crack growth, and I'm going to assume that the crack grows through a series of little material elements in front of it, a whole series of crack initiations, and so on and so forth. But when you look into what they're doing, they still base it on all the fracture mechanics solutions in it, and then they have something that correlates the growth rate. So I think that that's probably a fair statement. And it's the only real way of dealing with cracks. There are, of course, some limitations. The sequence effects can be a little bit complicated. And knowing the initial crack size is difficult, and it's, of course, difficult to deal with cracks that interact with plasticity to know how to do that. It's doable, but a little bit difficult. So I think that in order to do a good job, you have to worry about really getting the